Hello, this is the Mr. Dan Maths channel. Today I'm going to be specifically going over a very unique method that we learn in Further Maths, which is related to your sums of series. Particularly what it's going to relate to is a converging series, i.e. if I were to take the series to infinity, then this series would basically approach a number, and we can calculate, or rather deduce, this number by using this method. It's called the difference method, or more, I guess, fancily termed telescoping series. And it's usually used for when we're evaluating a sort of fraction, or a function that is a fraction. We have to first of all consider r equals 1 to, let's first consider it to m, just for simplicity's sake. We want to evaluate what's 1 over r times r plus 1. Crucially, if you were to expand this out and find what it exactly represents, you will get 1 over 1 times 1 plus 1, which will be 1 over 2, which is your first term, plus 1 over 2 plus 2 times 2 plus 1, which will be 6, plus up until some number n times n plus 1. And there's no foreseeable pattern in writing all the terms here, because ultimately the expression will just collapse down to this sort of rth term here. There's a smarter method, and it involves a little something called partial fractions. Partial fractions essentially is reversing the step that you were taught at GCSE, simplifying algebraic fractions down. So if I were to give you a fraction, 5x minus 9 over x plus 2 all squared equal, or I'll subtract it, minus 1 over x plus 3. And this would come up in an intermediate / higher tier GCSE paper. The key thing is you'll just cross multiply. So 5x minus 9 times x plus 3 minus x plus 2 all squared over x plus 2 squared x plus 3. What a lot of teachers refer this method to as is the kiss and smile method, because you are essentially just marking a cross over here and then you're multiplying your denominator straight on. Essentially what we're going to learn today is how we're going to reverse that process. So if I were to give you this fraction, maybe simplified down a bit, how can I get from this fraction to this fraction? Albeit maybe not as complicated as this. Fractions which have what are called linear factors in their denominator, you're not going to see more than 2 this year. At most maybe 3, but that was one standalone question. So it's rare that you'll see more than 2 linear factors. What I mean by linear factors, at least in your denominator, is I can see one number or one variable over here to the power of 1, and then I can see another function over here with the same variable to the power of 1, i.e. they're linear factors. Right, so let's start off with 1 over r plus 1. Crucially, what the interesting property about this fraction is that I can write it as the sum of the divisions of its linear factors. So I can write 1 over r times r plus 1 as something divided by r plus 1 plus something divided by r. This is a little bit easier to illustrate if you see fractions like, let's take a half plus a quarter. That will equal 3 over 4. Essentially, what you're seeing over here is that two factors of 4, which are 2 and 4, go to 4. Although maybe this wasn't that great of an example, but yeah, it's essentially the same idea. You have factors of the denominator over here, which you can split up into little fractions of their own, and then assign the numerator, which you do not know the value of, some parameter a, or b, or c. So that doesn't really matter there, what you name the numerator. But yeah, this is the form we will be working with. The easiest thing to see over here, okay, is to actually multiply both sides by the denominator over here. Because if you multiply the denominator over here, then you can get rid of the left-hand side of r times r plus 1, which is quite cumbersome, and actually simplify the right-hand side down a fair bit as well. So if you multiply r plus 1 on this side, and then r plus 1 on this side, what you end up with is 1 equals a times r plus 1 divided by r plus 1 plus b r times r plus 1 divided by r. Crucially, you don't really need to write this step down, because ultimately you can kind of just see by observation that some of the terms here cancel out, i.e. Essentially what the numerator is being divided by, that's the term that you leave out, and then you just multiply everything out. Then you get this relationship, a r plus b r plus 1. Now this is a very curious relationship, because although there aren't any unique solutions to this equation, we can kind of force some values, because with a and b, they're parameters. We can't choose what a and b are. If I were to write this in terms of like logical statements, I would say for all r, there exists a and b. So there exists some value for a and b for which this statement, for this statement, there exists some value of a and b which is true for all r. Sorry, the other way around. If we have r, if we start off with r, for every possible value of r imaginable, I maybe except special cases like when this may equal 0, like if r equals 0, then obviously this isn't possible. But yeah, for every single possible value of r within our constraint, there exists a value of a and b for which this equation is satisfied. And we have to find those values. The easiest way is to represent r as some value, or some placeholder value, which is really easy because it starts cancelling things out. Crucially, you can let r equal 0 over here for calculation's sake. That means that if you substitute in, you get a times 0 plus b times 1. Hence, b equals 1. Likewise, to cancel b out, you can get r equals minus 1. So just let r equal minus 1. Substitute in, you get 1 equals minus a. Thus, minus 1 equals a. What is left is substitute in to the original expression that we started off with, our a value and our b value. So what we end up as our final fraction as, or the sum of our final fractions as, is minus 1 over r plus 1 plus 1 over r. And this is where our method comes in, enough sort of preliminary work. It's called the difference method because there is a subtraction symbol within our sum of fractions. Hence why difference, because we're working out the difference between this fraction and this fraction. This is also why the series converges, because out of, well, a lot of the terms between 1 over r and 1 over r plus 1 actually cancel each other out. So it's a very neat method that you can kind of think about. This fraction over here is equal to this fraction over here. Okay, because we've just worked out, if we went backwards from like our GCSE methods, that we'll get this fraction right here. Likewise, if we apply our GCSE methods, like r plus 1 minus r divided by r times r plus 1, clearly we get the same fraction out of it. What I'm trying to get at over here is that you can actually write this sum as this expression right here. So you can just substitute in the sum of fractions that we just calculated. Therefore, your sum starts to look more like this. Then, ultimately, you can have your sum distribute between your fractions, and now we have to kind of look at it at a more fundamental, or with a more fundamental perspective. We have to see, well, what does this big sigma notation really mean? We have 1 over r from r equals 1 to n. Really, we're summing every value 1 plus a half plus a third plus a fourth plus a fifth plus up to some value 1 over n. So clearly this is the harmonic series plus 1. Interestingly enough, I said in a couple videos back that this series is diverging. And there's a very neat proof right here. This series is discrete and it's bigger than the, or it's rather an overestimate for the area under the graph of 1 over x. And if you work out the area under the graph for 1 over x, it's ln of x. That's a very standard result that you have to work with in your year 13, which is next year. With ln of x, if you were to substitute in any value of x, no matter how large the value, the function still keeps climbing. Essentially, ln of x is diverging, and because this is an overestimate for ln of x, or for ln of x, then this series has to also diverge. So a little bit of an aside there, but it's a very interesting reason why this series doesn't actually converge. However, if you subtract this sum from this, then it will converge, because you are removing a half. So that's my first term, a third, a fourth, all the way up to 1 over n plus 1 over n plus 1. I write down the terms just before the substitution for n. I write the term for n minus 1 and maybe even n minus 2, because I can clearly see right here that these are going to cancel out, plus the extra terms at the end. So what you're left with is 1 minus 1 over n plus 1. A follow-up question that you could be asked is, what is the sum to infinity of r equals 1 over r, or rather how the question's been phrased, 1 over r plus 1. Clearly this is the final result that you get if n is at the upper bound instead of infinity. But this can be rewritten. We can write a limit which is as n tends to infinity of r equals 1 of 1 over r plus 1 to n. What does the value then approach? And that would be the same as applying the limit here, which will be 1 over 1 n plus 1. The value of n doesn't affect the value of 1. 1 still stays 1. So you kind of move it outside the limit because it's unaffected, and then you consider what 1 over n plus 1 approaches. And the nice thing about this is that we can clearly see with our observation that the denominator balloons off to infinity, and you can write the limit, or it's quite common for the shorthand of the limit from, let's say, n to, as n tends to infinity, of 1 over n equals 0 to be written as 1 over infinity. So although not mathematically airtight, it is completely fine for you to write maybe 1 over infinity here. But this will just be 0. Therefore, this series tends to 1. Ultimately, some decently advanced ideas have been used here, but the application itself is quite simple. It's just the sort of explanation behind this is a little bit more abstract than any other topic that you should have encountered before. So, essentially, when you're dealing with limits, the kind of forms of infinity that you work with work quite well sometimes. So, I guess when you're in this form, 1 over n plus 1, then as n tends to infinity, 1 over n tends to 0, that is a perfectly plausible thing to assume. Although there is one distinction that you could make over here, and the astute among you might have already sort of alluded to this. It's what if it tends to minus infinity? Does it tend to 0 again? Yes, it does. And the very interesting thing about that is that's one of the reasons why 0 or any number divided by 0 is undefined. Because if I were to illustrate this using a graph, the graph of 1 over x, if you were familiar with it, looks like this. So it has asymptotes at y equals 0 and x equals 0. Clearly, if you were to, let's say, travel along the x-axis in this direction, as you get closer and closer to 0 from positive infinity, you start approaching, sorry, this is minus 1 over x. So this is what the graph looks like. Here, clearly if you're approaching 0 from the positive side, then things are going to shoot off to infinity. So let's say you have 1 over 0 over here. This is undefined as we know it, but why is it undefined? Because first of all, what my limit over here is telling me as I approach things from the positive side, I go to positive infinity. But if I approach the same value from the negative side, so minus infinity is here, let's say, then this value right here shoots off to negative infinity. So is the value or the limit as x approaches 0, okay, from either side, of 1 over x equal to plus infinity or minus infinity? There is no clear answer as to what that is. Therefore, the value 1 over 0 is undefined. At least within our idea of mathematics. Okay, I think that should sum up the difference method. There is a lot of expressions that you can use the difference method for. Crucially, the only condition that you need is one fraction subtract another, and it doesn't even have to be two fractions. There's been a question in the WJEC which involved 3 fractions or maybe even 4. So you kind of need to be prepared with the uncertainty of you having even more complicated questions to work with. But the premise of the question is essentially the same. You have to look at a partial fraction, you have to break down the partial fraction, essentially reversing your methods from your GCSE. And then, finally, you have to look at those 2 fractions, compare those 2 fractions expanded out in their respective sums, and then finally cancel like terms out until you get a final finite expression that you can work with, and that will be your answer. So in this regard, what this is called, telescoping series, is a pretty fitting term. So is difference by method, because telescoping series means it just goes down to one value right here, or one expression. So that's quite nice. Difference method, obviously, because you're subtracting fractions. So that is also actually I'll go through one more question, kind of illustrating this with maybe another example. So I think I'll go through the sum r equals 1 to infinity of 1 over r plus 1, r minus 1. So exact same steps as before. What you're required to do over here is observe this fraction that you're trying to sum and split it into smaller partial fractions. So this will be equal to a over r plus 1, because that's one linear factor, plus b over r minus 1. Later on in year 13, you'll look at more complex partial fractions, so ones that may contain like factorable quadratic maybe, or an unfactorable quadratic, or maybe the numerator is bigger than the denominator, i.e. it's an improper algebraic fraction. Ultimately, this is kind of like the basics, where it's sort of begun, and interestingly enough, in series of all topics, but there we are. Just like our previous question, where I introduced the topic, we'll just multiply both sides by r plus 1, r minus 1. So what we're left with on the left-hand side is just a times r minus 1 plus b times r plus 1. Crucially, it doesn't matter what order your a and b are, as long as they stay coherent throughout your answer, so that your final substitution is correct. So let r equal convenient values. The nice thing about this sort of expression is that ultimately it doesn't matter what values of r you substitute in, you can always work towards an answer. Because let's say you substitute values of like r equals 1,000,000 in. Inconvenient, but you could do simultaneous equations if you like, although I wouldn't recommend it. So this expression goes to 0 over here, and then it just adds to 2. So we have 1 over 2 equals b. So that's one of our values. Then you let r equal minus 1, so that we can let b times r plus 1 become 0. So substituting everything in, we get 1 equals times minus 2, and we can already see that we have a minus over here, and if we rearrange out, we can get value for a, which is going to be negative. Clearly we're going to be using difference by method, or yeah, the difference method again. Therefore, this kind of ambiguous expression, I say ambiguous because it doesn't have any values for a and b, becomes 1 over 2 minus at the front, r plus 1, plus 1 over 2 r minus 1. Of course, you can check if this expression is correct if you just expand outwards and arrive at the final answer, which is going to be the same. So, erasing all my scratch work here. And get started at the question. So, I'll just do that in red. Alright, so substituting this expression into my sum, what you will get is the sum to infinity of r equals 1. I'll just swap the minus and the plus around. So 1 over 2 times r minus 1 minus 1 over 2 r plus 1. Then, distributing the sum again, we'll get the sum to infinity from r equals 1 of 1 over 2r minus 1 minus the sum to infinity of r from r equals 1 of 1 over 2r plus 1. Of course, you can factor a half out of this whole expression so that you can get whatever it is in your brackets. So just a sum to infinity from r equals 1 of 1 over 2 times r minus 1 minus the sum to infinity from r equals 1 of 1 over r plus 1. But it isn't necessary, just a little insight as to how you can make the problem easier for yourself perhaps. But yeah, I think I'll actually leave the half out, just easier to do the arithmetic in your head that way. So, we'll start off with our first bracket, and crucially, if you want the mathematics itself to be really rigorous and mathematically airtight, I should say, is first of all you should write these up as limits, so that you can actually work with n at the end. Because realistically, if you just start substituting n in, then it's kind of like implied work, and obviously that's perfectly acceptable at A-level maths and further maths level, but it should be a good habit of yours to just be very mathematically airtight and ultimately just aim for the best workings out that you can give. So now I can write this as a limit n equals infinity of a large expression, a half times, and I'm just going to consider 1 over r minus 1 now because I factored a half out. So this should start at 2, sorry. It should start at 2 because if you have 1 over r minus 1 and then r equals 1, then your entire denominator becomes 0, and as we discussed before, that's a problem. Likewise, this starts at 2 as well. Alright, so everything correct over here. We start off with our expression. Of course, one thing that you should learn from seeing me do workings out over here is also check your workings out, because you never know where you might have swapped a plus and a minus. You never know where your upper and lower bound might be incorrect. So yeah, it's a lesson to take from this video. So starting off here, you'll have a third plus a fourth plus a fifth, all the way up to 1 over n plus 1. Alright. Sorry, just the working out was horrible. If we have 1 over 2 times r minus 1 over here, then you're going to start off with a half actually, because you're going to have 2 minus 1 and then r plus 1 over here. So it's going to be a half plus now 3, so it's going to be can't forget the first term, so it's 1 plus a half plus a third plus a fourth plus all the way to plus 1 over n minus 1. So checking again, 2 minus 1 is 1. 1 over 1, 2 minus 1 is just 1 over 1, 1. That's my first term. 1 over 3 minus 1 is 1 over 2, second term, done. 1 over 4 minus 1 is the third, fourth, fifth. Okay, yeah. So this is correct. Then I look at my second expression right here. So because I factored a half out of everything, I'm just looking at 1 over r plus 1. Now, if you have starting from 2, then you're going to start from a third over here, because 1 over 2 plus 1 is a third. Then you have a fourth, a fifth, and then all the way up to 1 over n minus 1 plus 1 over n plus 1 over n plus 1. Crucially, I write the last few terms just before 1 over n plus 1 so that I can actually see up until what point everything cancels out. So you have to be aware of where things terminate. So this entire expression collapses down. What you're left with ultimately is a half times 3 over 2 minus 1 over n, I'm going to keep this in brackets, minus 1 over n plus 1 over n plus 1, and then I'm just going to simplify these brackets down. What we'll get is 3 over 4 minus a half, and then this bracket goes to 2n plus 1 over n times n plus 1. Of course, I think it's a little bit easier if you want to evaluate the limit here, but if you were asked to just work out what the expression in terms of n was, then I would start simplifying down. The 2 doesn't cancel, just leaves a 2 just like that. Just moving here, you get, well, your final expression to be 1 times 2n plus 1 divided by 2n plus 1. And that should be the expression. Of course, the original question asks you, what's the sum to infinity? So we're actually going to go a step back over here, and we're going to look at this, and we're going to try and look at what happens when we take n to infinity. So clearly we're going to have 3 over 4, and the limit is from n to infinity, minus, and it's going to be 1 over 2n plus 1 over 2n plus 1. Clearly, if you substitute n equals infinity into all of this, you can kind of, use that interchangeably as the limit from n equals infinity to 1 over n. It's the same form over here. The denominator becomes extremely large, therefore 1 over the denominator, the reciprocal, becomes extremely close to 0. So if you just were to repeat this off for all of eternity, you will be arriving at the answer 3 over 4 minus some really small value, which is 0, and another very small value, which is 0. Ultimately, what this expression simplifies down to is 3 over 4. Another way to look at this is a reciprocal function, this is a reciprocal function. What do reciprocal functions have a form of? They have vertical asymptotes and horizontal asymptotes. At least with the principal reciprocal function, we have this, 1 over x, which has a horizontal reciprocal, or a horizontal asymptote at y equals 0, and a vertical asymptote at x equals 0. Crucially, this is because as x balloons off to infinity, y will go to 0. Likewise, if you have y balloon off to minus infinity, or x balloon off to minus infinity, y will go to 0 as well. So that's kind of how you can reason with these questions. If you're kind of unsure with how the limit might behave, then drawing a graph is a good place to start and kind of working from there. Although nothing in the exam I expect you to really draw a graph for. Ultimately, it's kind of pattern recognition, how these limits work at this level at the very least. I think that concludes the video. Thank you for watching as always. I'll see myself out.